So we're going to look at position versus time, velocity versus time, and acceleration versus time graphs. In terms of understanding how we can model a particle's motion using math, physics, graphs, things like that. So it's important to note this particle that we're particularly looking at, the modeled particle here, this is still one-dimensional motion. So the x-axis is actually going to be our input axis. That's time in this instance. Time is a scalar. So in this case, not always exclusively, but usually our time is set to seconds. Now, you want to pay attention to the units written. It's not always going to be that case, but for the most part, we're going to be using seconds. And then our position would be meters here. Again, not exclusively, but we will primarily use meters. And what we see is that this is essentially going to be the motion of a particle over 10 seconds. And we can kind of see some uniformity in terms of its motion. For the first case, we're going to look at from 0 seconds to 3 seconds. So at the origin, at 0 seconds, it's at 0 meters, which means we're just going to start it wherever it's at. We can kind of pick the origin system here for this, or it's just oriented at whatever we would call the origin. And it's going to start moving in the negative direction. Now, in terms of practical application, what that could mean, since this is still one-dimensional motion, the negative just assigns the direction because this is a vector in terms of the motion. So we have to deal with vectors here. If it's going left to right, generally we associate going to the right as positive, going to the left as negative. But it could also be up or down. It doesn't really matter here. But we could say, just for understanding and simplicity's sake, this is a particle that's starting at origin and immediately starts going to the left in terms of what that would look like. And after about 3 seconds, it has gone about 3.7 meters to the left. And at first, it was going kind of fast, and then it started slowing down. And I can show that it's slowing down with two really big relationships here. So the slope of this particle, I want to think, the slope of the position over time, just in straight up standard y equals mx plus b, our understanding of rise over run kind of slope, means that that's the position over the time, which is equal to the velocity of a function, right? So we denote for position time graphs the velocity as the slope for the function. The slope here is negative. So the velocity is negative, which means the particle's traveling to the left. That makes sense. That's fine. We understand that pretty well. There's another step to that, though. We'll see that the slope is not uniform. It's changing, which is why there's a curve. If it were a straight line, I'd expect to see a constant velocity. It's not changing. But if the slope itself is changing, well, the change in velocity over the change in time is defined as acceleration. And we see the sign of acceleration, if I'm not getting too much into the calculus here with this, and as the concavity of my graph or my curve. And what that means, again, without getting into the second derivative, is it bowl-shaped up or bowl-shaped down? In terms of, that's what concavity is. I mean, you can think of like the bottom face or top face of a cave. And in this case, it's slightly curved like a bell upwards, which means it's concave up. If it's concave up, that means that there is positive acceleration. If the velocity is negative and the acceleration is positive, so those signs are opposite each other, then that means a particle will be slowing down, because you can think acceleration is working against velocity here. So from 0 to 3 seconds, the way I would describe this motion is particle starts at origin, is going fast, and then slows down, traveling to the left, or traveling down, however I would want to say that. And then I can look at the motion from 3 to 5 seconds as kind of the opposite. Now it's still traveling to the left, or whatever the same negative direction I've set up is. But in this case, so the velocity is still negative because the slope of the graph is still negative. But this time we see the concavity is flipped. That curvature of the concave roof, so to speak, or the curve is now pointed downwards. So if it's concave down, this is the same direction. Concave down is negative. If velocity is also negative, acceleration is negative. The signs are the same. That means they work together, which means the particle would now be speeding up. So slowing down from 0 to 3 seconds, from 3 seconds to 5 seconds, it is speeding up. It is still going to the negative direction. And then it looks like it instantaneously changes its motion at around oh goodness, what is that? 14.6 meters, which is at 5 seconds, and it starts to travel backwards. So now this is a slightly positive slope, not much. But if I look from 5 to 7 seconds, it's a little bit of a positive slope. Well, if it's a positive slope, that means it's positive velocity. It now, all of a sudden, it instantaneously changes going a little to the right. And that's a straight line. That's a very straight line. So we see the slope is positive. The slope is not changing, which means its acceleration at this specific point is 0. So that's what I should expect when we look at the velocity and acceleration time graphs. But then let's look at, now this is subtle. I maybe should have put a better fraction for this in terms of the graph, but this is a slight curvature. I'll just tell you that. It's a slight curvature here from 7 seconds to 10 seconds. So it's slightly concave up, and it is a positive velocity. So the motion of the particle then would be continuing to go to the right this time from 7 to 10 seconds. It has a positive velocity, so again, going to the right, and it has concavity that's up, so positive velocity, positive acceleration, working together, meaning speeding up. So let's break it down again. 0 to 3 seconds, I'm going to the left. I am slowing down. From 3 to 5 seconds, I'm still going to the left, but now I'm speeding up. From 5 to 7 seconds, I am now going to the right, and I'm traveling at a constant speed. And then from 7 to 10 seconds, I am going to the right, and I'm speeding up. And that's how I would kind of break down the motion for this graph. And we can verify that by looking at the velocity versus time graph. Again, without going too into the calculus of this, the velocity of time is kind of modeled essentially as the first derivative of the graph. Now, I'm going to keep them overlaid with each other for a second just so we can kind of see it. So from 0 to 3 seconds, we see the velocity is below the x-axis. Now the velocity slope is positive. Now remember, the slope of the velocity is the acceleration. So what we had said was positive acceleration from 0 to 3 seconds because it's concave up. We see that from the positive slope in blue, which is the velocities equation. So that's how those two relate. The velocity starts at negative like 2-ish and then goes a little less than -1. So it's slowing down, which is why the velocity gets less negative. Its direction matters, but the fact that the quantity of it gets smaller means it's slowing down, which is what we had kind of determined from 0 to 3 seconds. Then if I look at 3 to 5 seconds, I have still negative velocity. You'll see an instantaneous change in the velocity there, but I have essentially that negative velocity, and it looks like it's going faster, right? So the velocity slope is negative. The velocity is negative. We said the acceleration should be negative. The velocity should be negative. If they're both the same sign, they should be speeding up. And that makes sense. I see about -3 meters per second is the velocity starting about here. And it increases to almost about 8.3, right? So it's getting faster in the negative direction. And then from our 5 to 7 seconds, right down here on this graph down here, we saw we have a positive velocity, but it is the same. It's constant. So I see I have a slightly positive velocity here with the same slope. It just stays at 0.125, whatever that is. Doesn't have a slope. And if the slope of the velocity graph is acceleration, if the slope is 0, then acceleration isn't occurring, which makes sense. The velocity is not changing. It's constant. And then from 7 to 10 seconds, all of a sudden I have more positive velocity, which we kind of see. And it is increasing, again, positive slope, positive acceleration. So then again, we see that speeding up. And I can model the acceleration in green to see how that changes. I have, and this should directly equate to the concavity of the red function, the slope of the blue function. So in the red function, the position, 0 to 3 seconds, concave up. The blue function, velocity, time, positive slope. So I see I have this green bar of some positive acceleration right here. Then from 3 to 5 seconds, concave down, negative slope. So negative acceleration, which is what I see. And in fact, actually, the acceleration itself is changing. And then from 5 to 7 seconds, we had no changing velocity, right? So the velocity was constant. That shows us a 0 acceleration right here, which is what we expect. Then again, so 7 to 10 seconds concave up, positive slope, we should expect to see positive acceleration, which is what we see right here. So that's how we would kind of relate each part and comparing a graph with position, velocity, and acceleration to understand how a particle's moving.